AP Physics, we're continuing our lessons in rotational and circular motion. So in this unit, we will look at rotational motion and its analogs with translational motion. In this context, an analog is an equation in translational motion that has a related equation in rotational motion. Translational or linear motion is based on a change in position, also called the displacement, delta x, moving from one point to another in a straight line. So this would be an example of that right there. You have to be going to two different positions in space. Rotational or circular or angular motion is based on a change in angle, that's change in theta, moving around a circle. So here you see that going around like that. That would be rotational motion. Linear velocity is how fast an object travels between 2 points in a straight line. If the object does not speed up or slow down, the velocity is constant. The formula for average linear velocity is velocity equals displacement delta x over time, or if it's in a straight line, distance and displacement are the same thing, and so we can call it d over t. Angular velocity is how fast a circle or wheel turns. As long as the wheel turns at the same number of radians per second, the angular velocity is constant. The formula for angular velocity is omega, the Greek letter omega, equals change in theta, that's the change in angle, over time. Theta is measured in radians, and so you just have to remember that 2 pi radians equals 1 revolution around the circle. Linear velocity is given by velocity equals displacement over time. So the box moves 4 meters per second in 2 seconds. Velocity is 4 meters over 2 seconds, which equals 2 meters per second. There's the box it was referring to, and it goes across at a constant velocity. Angular velocity is given by omega equals change in theta over time, where theta is measured in radians. Remember, 2 pi radians is 1 revolution around the circle. So example, the box moves around this wheel 3 revolutions in 2 seconds. What is the angular velocity omega of the wheel? So omega is delta theta, change in theta over t, 3 revolutions in 2 seconds. Now you need to convert that into radians. So there's 2 pi radians for every 1 revolution. Revolution cancels, and you get 6 pi radians over 2 seconds, which is 3 pi radians per second. So that's 1.5 revolutions around the wheel in 1 second. Let's look at uniform circular motion on the wheel to the right. Angular velocity omega is how many turns in radians the wheel makes per second. So both A and B move 5 revolutions in 15 seconds. So they have the same angular velocity omega. So omega equals change in theta over time. So it's 5 revolutions in 15 seconds. Again, convert to radians. 2 pi radians is 1 revolution. That cancels, and you get 0.67 radians per second is the angular velocity of both of those. Both A and B have the same angular velocity. Tangential velocity is given by the formula velocity, that's linear velocity, equals omega times the radius. So now the fact that B is farther away from the center of the circle makes a difference. So for point A, it's 1 meter from the center of the circle. So V equals omega R. So it's 0.67 radians per second times 1 meter, and that gives you 0.67 meters per second. For point B, it's 3 meters away. So same formula, 0.67 times 3 meters equals 2 meters per second. So B is moving faster than A tangentially, but angular velocity is the same. Another view of the angular velocity omega computed on the last slide is demonstrated to the right. So there is the formula again. And there are the two calculations that we came up with. So it's going to look like this. They're going to go around. The tangential velocity vector is always pointing straight ahead at whatever point the two objects are. But for B, it's a longer vector because it's moving faster. It's moving faster. Its linear velocity or tangential velocity is faster than A's. Angular velocity is the same. Tangential velocity is greater for the object that's farther from the center of the circle. Linear acceleration, A, is this change in speed, either speeding up or slowing down. Linear acceleration does not involve a change in direction. So this is the type of acceleration we've been dealing with all year. So there's the formula. Acceleration equals change in velocity over time. So here's the box is speeding up, and here the box is slowing down. So those are both examples of, or the two cases of linear acceleration. Okay, a change in direction produces angular acceleration. So we see the wheel is turning at a constant velocity. Now, if a torque is applied to that wheel, a torque is a circular force. So it's going to cause the wheel to speed up. So it will go around now it will go at a constant velocity, and then a torque is applied against it. That will cause it to slow down. So the angular acceleration, either speeding up or slowing down in how fast the wheel is turning, is caused by a torque that's applied to it. So there's angular acceleration equals change in velocity over time. Angular acceleration occurs when a torque, that is a force that causes an object to rotate, increases or decreases the angular velocity omega over a time interval. This means the wheel will spin faster or slower than it was before. Torque is the rotational analog of force. When the wheel is speeding up, there is an angular acceleration. If there is an angular acceleration, then both points A and B will increase their angular velocity by the same amount and will have the same angular acceleration. So tangential acceleration or linear acceleration equals angular acceleration times the radius. So let's first look at the angular acceleration. So they're at different distances, but the angular acceleration of these two is going to be the same. Okay, so they're both going around, they're both speeding up in a circular fashion at the same rate, at the same angular acceleration. The linear acceleration will be greater for point B than point A because of the greater radius. So the linear acceleration is those arrows right there. That's the tangential or linear or translational. Those all mean the same thing, acceleration of that wheel. So here's an example from your textbook, example 10.1 in chapter 10. Part A, a teenager puts her bicycle on its back and starts the rear wheel spinning from rest, meaning 0, to a final angular velocity of 250 revolutions per minute in 5 seconds. So there you see the wheel is starting to spin, it's speeding up, and it finally gets up to where it's going 250 revolutions per minute after 5 seconds. So state what you want to find. We want to find the angular acceleration of this. What's in the toolbox? That means what numbers are you given? So omega, the angular velocity, is 250 revolutions per minute. We need to convert this into radians per second. And the time is 5 seconds. So step 3, identify the formula or formulas. So it's going to be angular acceleration equals change in angular velocity over time. So you set up the equation and solve it. So there's the angular velocity. It's 250 revolutions in 1 minute. We're going to multiply that by 2 pi radians per 1 revolution. And then we're going to change from minutes to seconds because there's 1 minute for every 60 seconds. So revolutions cancels there, minutes cancels there, and then you end up with units of radians per second, and that's what you want. So it's 26.17 radians per second. Now it does that in 5 seconds. That's the angular velocity, but it's changing by that much in 5 seconds. So the angular acceleration is 26.17 radians per second divided by 5 seconds. So that gives you 5.24 radians per second for every second that goes by. That's its angular acceleration. Okay, now we're moving on to part B of the same problem. If she now slams on the brakes, causing an angular acceleration of negative 87.3 radians per second squared, how long does it take the wheel to stop? So step 1, state what you're trying to find. You're trying to find the time. How long is it going to take for the wheel to come to a stop? List what you are given or calculated. So the initial angular velocity that we calculated in part A was 26.17 radians per second. Now we need to have the final, and that's going to be 0 radians per second. It's going to come to a stop. The angular acceleration is negative 87.3. And this is just a note, kind of as an aside, that you should really learn to quickly convert from revolutions per minute to radians per second. So if you just want the shortcut, you could just memorize this. It's whatever revolutions per minute. I'm just using 100 as an example here. Times 2 times pi divided by 60, and that will give you the radians per second. So that would be 10.5. That has nothing to do with this specific problem. It's just a note that you should do. Okay, anyway, continuing. Step 3, find the formula, substitute, and compute. So there's the formula for angular acceleration, and it's the angular velocity divided by the time. Okay, so now we're just doing algebra. The solve for time, multiply both sides by time, cancel on that side. Okay, now you divide both sides by alpha, by angular acceleration, cancel on that side, and you get time equals change in omega, change in angular velocity, over angular acceleration. Okay, so the change in velocity, angular velocity, is the final velocity minus the initial velocity. So the final is going to be 0 in this case, and the initial, what it was going at the beginning, is 26.2. So when you subtract those, you get a negative 26.2. And that's over the acceleration, which is slowing it down. That's negative 87.3. So that gives you a time of 0.3 seconds. Tangential velocity is the same as linear velocity. The tangential velocity, V0, of the wheel is equal to the angular velocity, omega 0, times the radius of the circle. If the angular velocity is doubled to 2 omega, then the tangential velocity is doubled to 2v, if r remains the same. You can double v by doubling omega, or by keeping omega constant and doubling r, the size of the circle. Tangential velocity is the same as linear velocity. The tangential velocity, v tangent, of the wheel is equal to the angular velocity, omega, times the radius, r, of the circle. So there you see an example of that. Omega is how fast the wheel is turning in radians per second. One time around the wheel is 2 pi radians. R is how big the wheel is, its radius. If you multiply how fast the wheel is spinning by how big the wheel is, you will get the tangential velocity. The tangential velocity of a bike wheel equals the linear velocity of the bike as it moves down the street. So if you know the tangential velocity of that wheel, that tells you the overall velocity of the entire bicycle moving down the street. Notice you could double the tangential velocity and the linear velocity of the entire bike by doubling how fast the wheel is spinning, that's 2 times omega, or doubling the size of the wheel, 2r. Under uniform circular motion, that means it's going around at the same speed. Both angular velocity omega and tangential velocity remain constant. The only acceleration under uniform circular motion is the centripetal acceleration pointing towards the center of the circle. That's AC. Under uniform circular motion, both omega, angular velocity, and tangential velocity are constant. The centripetal acceleration is given by the formula centripetal acceleration equals tangential velocity squared over the radius. Linear acceleration A is caused by a change in speed, and that's linear, so this is just comparing the two. So that's final velocity minus initial velocity over time. That's the kind of acceleration we've been dealing with all year. Centripetal acceleration AC is caused by a change in direction, so that's the tangential velocity squared over the radius. Angular acceleration alpha is the change in angular velocity, delta omega, in radians per second. There's the formula there. Alpha equals change in omega over t. Tangential acceleration A, the kind we've been dealing with all year, linear, of the wheel is equal to the angular acceleration alpha times the radius r of the circle. And there's the formula for that. So if an angular acceleration alpha is increased, the tangential acceleration will increase by r times alpha. The tangential acceleration alpha is a linear acceleration, and it is the same as the translational acceleration of the bicycle it is attached to. So here's a table that gives you an overview of these relationships. So for displacement, linear is delta x. Angular, we're talking about theta, how many radians around a circle that the wheel turns. And the relationship is delta x equals the radius times theta. Velocity displacement. The velocity in linear, what we've been dealing with all year, is delta x over t. And omega, the angular velocity, is equal to change in theta over t. It's how many radians around the wheel is going each second. And the relationship between the two is that linear velocity equals angular velocity times the radius. So you're starting to see some patterns here of how these relationships work. Acceleration. So acceleration, linear, the type we've been dealing with all year, is change in velocity over change in time. For angular acceleration, it's alpha equals change in omega over time. And the relationship between the two is linear acceleration equals angular acceleration times the radius. Velocity and acceleration. So the final velocity equals acceleration times time plus the initial velocity. And for angular, the final angular velocity equals alpha, the angular acceleration times time, plus the initial angular velocity. And there's a similar relationship between velocity and angular velocity. And for force and torque, force equals mass times acceleration. Torque equals force times the radius, that is the distance from the center of the circle. And that's the same formula there. Okay, so you see some of these relationships and the patterns between them. All right, and that takes care of this next lesson on rotational and circular motion.